before I start, I just want to say this really, Simao should be the one starting this workshop, and he very kindly, because I had a conflict, and he very kindly accommodated my schedule for me to be here. But I think I just want to start by congratulating Simao on this, and for all of us here at Rice, this is a great opportunity. So I will introduce myself. I'm Ming Yi, and and we have a spectroscopy group. We mostly work on correlated materials, topological materials. And today I just want to give you a flavor of the various projects we've collaborated with my colleagues here at Rice. And I'll talk about geometrically frustrated quantum materials, and specifically for those that where we can find some emergent bases. Okay, so okay. Before I get there, maybe I should probably introduce some of the things that we do in our group. So we're primarily an RPS group. We use Ingersoll photon emission spectroscopy to look at various types of quantum materials. We have our own lab in Brockman Hall, and we also travel to national facilities to carry out RPS measurements. So up until last year, we mostly collaborated with our single crystal growth friends, but last year we put together this MB chamber attached to our RPS chamber, in which we can grow some thin films and start to look at some of these materials in situ. On the bottom here shows also our interest in developing various kinds of sample environments for in situ tuning of quantum materials and phases, ranging from surface treatment to play around with topological surface states to in situ tunable uniaxial strain, which is developed for both our own system as well as our several beamlines, where we can use a continuously tunable strain to look at pneumatic phases, for example, nictides and other materials. And then very recently, we're very excited about this development as we start to look at the possibility of measuring band structures under a finite magnetic field, which until recently was never possible. So I think this is another direction that we're very interested and excited about. So maybe next time, maybe next year, I can show you some results that we have in this talk. Okay, so what am I here to talk about? So this week, we just had this wonderful workshop talking about flat bands. And I don't think I need to introduce too much in this audience, but the start of the workshop started with just about graphene and various kinds of 2D materials. And for maybe the younger audience, the way you can create these flat bands is by twisting two-dimensional flakes. And by twisting, you can fold bands and therefore create these really flat bands. And then if you tune them to the Fermi level, then all kinds of emergent phases appear, right? So this is how they play around with 2D materials, and these really exciting developments we just heard about this week. But there is one problem, which is that these are typically very small materials, and so far not quite accessible by the many types of bulk experimental probes that have been developed over the past decades to study correlated materials. So a lot of us can't really join the fun in this area. So what do? We got to think about how in bulk materials, are there ways we can construct this kind of flat band physics and then look at some of these properties with all the probes that we have already developed for bulk materials, right? So there is a way to do that. This is known as what's called the geometric frustrated lattices, and the poster child, which is the one on the slide, is that of a Kagome lattice. So this is a picture of a Kagome lattice. It's formed by these corner sharing triangles. And the key interesting thing about these is that there is a exact cancellation of the nearest neighbor hopping. And the consequence is that there therefore cannot be hopping outside of these hexagons. And this forms what's called compact localized states. So the way to think about this is that if you quench completely the electronic kinetic energy, that means your band in momentum space would have zero bandwidth. So in other words, if you think about in momentum space, this will give you these so-called flat bands, right? So just like the case of twisted bilayer graphene, in bulk materials, there are such materials that give this kind of geometric frustration that lead to these flat bands, right? So this is one way that the community has come together to think about and realize recently in many types of materials. And I just want to say, not only is this special to Kagome lattice, but this is actually a method that works for any so-called line graph lattices. And you can see that here, this Kagome lattice is a line graph lattice of the honeycomb lattice, which is the stuff which you can see underneath. Right? So this is one methodology that we can design bulk materials or search for bulk materials that exhibit such kinds of flat bands. And this has been demonstrated by ARPES. So this is a paper published, I forget which Nature journal, but it's one of these Nature journals that of cobalt-tin, and cobalt-tin is maybe a vegetable, a Kagome material that is not being ordered, and however, you can see very clearly there's these flat bands that appear in these band dispersions that correspond very well to this DFT calculation. These are the Kagome flat bands, which derives from this kind of picture. Right. Great, but there's one problem with this kind of thing. If your flat band is so far away from the Fermi level, really all you can do with it is look at it with ARPES, and it doesn't really affect any of the low energy physics. So we really got to find materials where the flat band is also appearing at the Fermi level, and therefore can actually make a difference in terms of its magnetic properties, electrical properties, and so on and so forth. Right? Other people may be interested. So to do that, we have to look around in our bulk materials and find candidates that would have this kind of geometric frustration, and people have done that. So over COVID, there are groups who have gone through SCSD database, try to search for all the known crystal structures and look at the various types of geometric frustration lattices. And these are the top most common lattices that gave you this kind of flat bands, right? So these are the winners, the Kagome lattice, followed by paracore, and so on and so forth, right? So there's actually a lot of materials in bulk that will give you this kind of flat bands. And then the next question is, once you find these candidates, we've got to find the ones where these find ways to push the flat bands to the Fermi level to make an impact on the low energy physics, right? So this is sort of the thought process of how we can look for materials that may exhibit interesting exotic bases. Okay, so that's the brief introduction. Our group has, in the past 2 years, worked on a lot of different materials from our friends, and these are the three lattices that we looked at in two dimensions, Kagome lattice, and then in 3D paracore lattice, and then this clover type of bipartite lattice. And I just list you the kind of the compounds that we have worked on in these three categories, and I won't attempt to tell you about all of them, but what I will do for this talk is I will give you one example out of each to show you what we have done by searching for the flat bands, and what are the consequences of the flat band to its low energy physics. So let me start with the leftmost one, which is the Kagome lattice. So I already talked about the flat band, which comes from this geometric frustration. In addition to that, if you do the tight bending calculation, considering only the nearest neighbor hopping, besides the flat band, you will also get 2 copies of dispersive states. And the distinct features of these is that these two bands would cross at a Dirac point and the K point in the Brillouin zone. And then in addition, you have this thing, which is the saddle point. So it's electron-like along one direction, and hole-like along the other direction. And the nice thing about this is that if you look at its density states strictly in the 2D limit, it will be a divergent density state. So you can think about if you tune your Fermi level there, then that can also give you some sort of electron instability. Beautiful. So our community together has worked on a whole bunch of Kagome materials in the past couple of years. And if you look around amongst these materials, there are 3 phenomena that have been identified, right? You can have superconductivity in some, charge density wave in some, and then magnetic order in others. And if you think about this, actually the very first prediction, maybe theoretically, the very first thing you think about is that once you have the flat band near the Fermi level, right, that will give you a huge density state, and it needs to do something, right? It must do something. So the zeroth order prediction is that this kind of large density state will give you a ferromagnetic order into this donor instability. And I think even given all of the amount of work people have done on Kagome materials, nobody has yet at this point answered the question for what happens when your flat band is at Fermi level, and then how or if this is related to magnetic order, right? So it's great. This is the first question, not first, but this is a question we thought we should think about how to do. So in order to do this, we have to pick a compound that is relatively simple, that has only a magnetic order and nothing else, right? Because we want to answer the question, what does the flat band have anything to do with this magnetic order? And to do this, my postdoc Zheng Ren and built together this MBE system together with my graduate student, was shared with Nanya, and they built this MBE system to grow some simple Kagome metal films, and this is the first material they grew, which is iron tin grown on STO. I don't know anything about MBE, so they really did this all together themselves. And so what they can do is that they can grow this film and then transfer directly to the ARPAS system and measure the electronic structure. It doesn't look as grainy on my laptop, so the data quality is actually better than the books. This is the Fermi surface, and the basic property is that this material, iron tin, if you think about it, it's layer material, and each layer has a iron Kagome lattice, and below 370 Kelvin, the moments on iron would order. They would order ferromagnetically in each layer, and then they're anti-aligned as you go along the z-axis. Simple, right? So the question we want to ask ourselves is, what happens to the band structure as the system goes through the magnetic order? And I just want to say this thing existed in single crystal form for a while, but the difficulty with the single crystal is it turns out that for ARPAS, it's very difficult for them to actually stay clean as we do this measurement. And the thin film, for some reason that's unknown to us, is really, really robust. So if we measure the film with ARPAS, we take it out to the other chamber, keep it there for a week and put it back in the chamber, actually all the features are reproduced. So this turns out to be a very robust system to look at actually what happens in the magnetic order as we what happens to the electronic structure as we ran through the magnetic order. Just to tell you the key message of this work, I want to illustrate this with the density functional theory calculations done by Ming Yi, who is on his way here. So Ming Yi's group at Weizmann did the DFT calculation, and to make a complicated story simple, if you think about, look at this plot, which is a plot of the calculated density states. This is for the paramagnetic state, and you see this large peak at the Fermi level. If you look over to the spaghetti plot here, this peak here corresponds to the Kagome flat band. These are the Kagome flat band. So this is a system where if you don't have magnetism, this is where the chemical potential is actually at the Kagome flat band. And then when they calculated the AFM state in this order state, they see that this peak gets split into two. So how do I understand that? The way you think about this is the following. So if you consider each of these layers, it's a ferromagnetic layer. Then you can project the band structure into the spin majority states and the spin minority states for each layer. And then you can see that here, this flat band is indeed split into a lower part and upper part. So effectively, the picture that emerges is the following, at least on the DFT level, is that in the non-magnetic state or paramagnetic state, high or non-magnetic state, very high temperatures, this is the flat band at the Fermi level. And then when the magnetic order appears, then you have a exchange splitting that opens because of this magnetic ordering. So you have a set down and set up. Right. So then the next thing we need to do is actually measure the band dispersions as a function of temperature. And so to make a long story short, we do indeed observe the states that match with the DFT that corresponds to spin minority states and the spin majority states. And as you ramp temperature, we can clearly see that they shift in opposite directions, exactly as we expect for this kind of picture. The only difference is that the amount of shift here we observe experimentally, that's a screen bar here, it's actually a tiny portion of the expected exchange splitting from DFT. So effectively what this means is that instead of the Stoner picture where you expect the band to split exactly across this transition, here what we see is that the exchange splitting actually remains above Tn. right? Okay, so this actually is very reminiscent of the picture you would get from a local moment ferromagnetic order. Except here, the distinction is that this is a situation where we actually cannot write the flat band into an atomic localized state. Instead, what we have here is a compact localized state. And then Qimao, I guess, in his talk, we talk about a part of this, how to think about this. But here, effectively, what we're seeing experimentally is that this compact localized state can effectively act like a molecular local moment that mimics that of atomic local moment that we have in the normal local moment picture. So this is the nature of the magnetic order we have seen. That'll be brief in the next couple of slides. Actually, I won't talk about iron germanium because I think Peng will talk about this. I'm going to skip this. And going from 2D to 3D, Jian also talked about this in the workshop, so I won't spend too much time on this. But the exact same thing happens in 3D. You actually had two copies of flat bands. And here, experimentally, we observed this in this material, copper, vanadium, sulfur. Here, the vanadium sublattice form this pyrophore, and experimentally, we see this extremely sharp and flat band right at the Fermi level. And the consequence, as he already demonstrated, is that there is a parallel behavior of the geometrical resolutivity that deviates from a liquid. So because he already talked about this, I will actually skip this as well. So that gives you a flavor of things we work on the Kagome lattice and the pyrophore lattice. And the last example is the Clover bipartite lattice. So this one, the community has worked on a lot. This one really came about because Qimao and his group, Chen came to us one day and said, forget about Kagome, and the new hot thing is pyrophore. So that they actually identify material candidates that will actually give you this kind of physics, and they convinced Peng to grow the crystal, and then we made the measurement. So this is great. This is a different story. The last example I'm going to show you, which I think is maybe a fun one, was really an accident that we discovered in the measurement. So this is the last one. Before I go there, both these examples are stoichiometric compounds, right? There are, the crystal structure is very clean. The last example actually demonstrates another way to realize flat bands in bulk materials. That's by vacancy ordering. So if you consider something we know and love, this is the honeycomb lattice, right? You can think about the red one and the yellow one being two different types of flavors of atoms. If you think about punching some holes on this lattice, and you punch it in an ordered fashion, you can actually change the crystal symmetry and create something that's called a bipartite lattice. And bipartite lattice means that the nearest neighbor hopping is always between the two different sublattices. And for some subset of bipartite crystal lattices, you can actually also get flat bands. I'll try to talk about that in a bit. So you can think about this is third example is example where using vacancy ordering, you can actually realize a new dimension for realizing flat bands in bulk atoms. So to make a long story short, what I'm going to show you in the following slides. This is it. This is the punchline slide. I'm going to show you this material, which is a van der Waals ferromagnet, iron 5 germanium tellurium 2. And what we can see is that we can actually switch back and forth reversely between two phases, in which case you have a vacancy that's not ordered and a vacancy that's ordered. And the consequence that this completely changes crystal symmetries and give you very distinct electronic structures and topology. And the really nice thing about this is you can go back and forth in a very simple thermal method, and I will show you this. So this is what I'm getting at for the third example. And
you have 5 minutes.
Okay. Okay, that's good. Okay, so I'll do this in 3 parts. I will first introduce a little bit of background of this. What is this iron 5 germanium tellurium 2 and why it's interesting, and then show you our results, and then lastly show you what's the consequence of the flat bands that we see in this system. So iron germanium tellurium has been around for a couple of years, and the most interesting thing about this a couple of years ago is that this family of van der Waals materials, people have demonstrated if you exfoliate them to the monolayer regime, you can still retain the long-range magnetic order, which is really interesting because this is one of the first example platforms for studying two-dimensional magnetic order, which wasn't around until a couple of years ago. So today I'm only going to focus around this last number, which is iron 5 germanium tellurium. And not only because its TC is high, but it has this additional degree of freedom of vacancy, which we can tune. And that is the key to all of this flat band tunability. To demonstrate this, let me walk you through the crystal structure. This is a TEM image, cross-sectional view. This is the unit cell. So this unit cell has 3 layers, ABC stacking of each of these van der Waals slabs. If you zoom into one of these slabs, this is what you would see. And if you stare at this long enough, you will realize this is inversion symmetric. And we'll show you this with pairs of arrows. The center inversion center is right here between the blue dots. Tellurium is obviously inversion symmetric, right? And then you have 2 pairs of iron. These are fully occupied, they're inversion symmetric. The key to this whole business is the last pair, which is iron 1. And if you have exactly iron 5, germanium tellurium, then between each up-down pair of the iron 1, only 1 can be occupied. Okay. And it turns out you can put the sample in the crystal into 2 phases. Either you have a complete random up-down occupation of the iron 1 side, in which case we call this the random iron 1 side order, or you can have a ordering of this in this up-down occupation. You can see the symmetry of these 2 is obviously different. And if you look at the in-plane view for these 2 phases, this is exactly what I showed you before. This is this honeycomb lattice. This is 50% occupation of the iron 1 side. And on the right, you have this this lattice, which has this clover repeating units, right? This has been demonstrated with STM. And the nice thing about this is that it turns out that depending on the last cooling step, if you quench it, the system prefers to be in this state. If you slowly cool it, it prefers to be in that state. If you're interested in knowing how that is, I can talk to you later about that. So what do we see? Because of the distinct symmetries, we measure the RPES. Oh, before we do the RPES, we want to make sure our crystals are actually correct based in the correct phases. So we reach out to the Liang's group at UPenn, who measured the second harmonic generation, which is a technique that directly probes the inversion symmetry of a crystal. And what they see is that indeed, in the site ordered phase, they have a very clear signature of inversion symmetry breaking. You can see the inversion symmetry is broken, and the other one, they don't. Okay, we've done other techniques. I won't have time to talk about them. So the punchline is that if you stare at the band structure here, they're completely different. And there are 2 key features that are different. In the site order phase, we see these very flat states. Thing and then with the thing across most of the Borean zone. In the other case, we don't. So that's difference number 1. Difference number 2 is that in the site disordered case, we also see topological band crossings. I won't have time to talk about that today, but I can also tell you more about that later. I'll only focus about the flat band part. Okay, let's look at flat band. How do we understand the origin of this flat band in this clover lattice? Here we have a lot of help from Chimel's group, and we look at this for a long time, and this is what we figure out eventually. So here is the repeating unit of this clover lattice. And this clover lattice is also a type of geometric brushing lattice. The phases will cancel such that there's no hopping out of these clover lattice. And this is also a bipartite crystal lattice. And the key thing about this is that the number of sites that belong to the red sublattice and the yellow sublattice is different by 1. And that 1 guarantees that you will have the existence of flat band. And that's exactly what comes out in tight binding calculations. And if you include silver coupling, this will become gap, and then this becomes a term from that. Okay, so then we can understand why we can only see this flat band in this bottom case, because in this case is only the case where you can see the destructive interference. When you don't have this vacancy ordering, that destructive interference is actually turned off, and therefore we don't see the flat bands in that case anymore. So this is actually a very cool case where you can directly see the effect of destructive interference in the same crystal. Okay. I'm almost okay. I will skip the switching part, and I will just show you one last thing. What is the consequence of this? In the consequence of this, if you look at the TC for this material, they're also different depending on which phase they're in. The one with the flat band actually has a higher TC. We've also done spin resolve RPES and see that the flat bands actually merge together across TC, and they're spin polarized. So this is actually a very nice example of the flat band actually responding to the ferromagnetic. Control is getting very. I'm gonna skip some. So the key message here is that in this example, we see that by playing around with this vacancy order, they can induce a destructive interference that can be turned on and off, and then there's direct consequence on the magnetic property of the material, right? So just to make the last pitch, this example demonstrates that beyond single crystals, we can also think about finding materials that have these natural vacancy orders as a way to tune the electronic topology. And I will start with the last slide. So when I was making the slide, my daughter saw this is a VBFF Symposium. She asked me if this means very best friend forever. And it takes a lot of people to do this. A lot of people here at Rice we've worked together with. We're very thankful for all the collaborations here locally and also around the world, especially Sunil's group for the theory. And I won't have time to read off all the names. So thank you very much.